Hello, welcome back to another session on in the series Digital Circuit Design using ADS. And today I am going to pick up a flip-flop design, right? And flip-flop is a basic element for a sequential circuit. Now, the difference between latches and flip-flop is very simple. Flip-flops, right? They are going to be edge triggered. So if there is a clock has got two edges, the rising and the falling edge, so you can have a negative edge triggered if the what you call if the transition takes place at a falling edge, then it's called negative edge triggered. If the transition takes place at the positive edge, it is called positive edge triggered. In case the latch in case of the latch, the transition can take place during a certain level, which may be a positive or a negative level. So the difference between latch and a flip-flop is latch is level triggered while flip-flop is edge triggered. So we are going to design a basic element. So in your project you create another folder. Let's call it flip-flops, and D flip-flop is the basic element for a sequential circuit. And what is a D flip-flop? D flip-flop is the output response to the input at a certain edge. So that will be called a D flip-flop. Now there are two ways to do it. One is you can use a master slave. So basically a master responds to one of the edges and the slave responds to the other edge. So this is a master slave configuration. The other one is you can just design based on delays and feedback loop. You can design a flip-flop. Okay, so let's start with a very simple implementation. So now I need a 3-input NAND gate. So first I will take a static gate and modify it. So I'll do it for both medium speed and high speed, right? So I'll pick up a NAND gate and say copy cell, and here I am going to change this to be NAND 3. So NAND 3, and I'm going to copy this over here, and in this NAND 3 I'm going to add one more transistor in pull up as well as pull down circuit. Okay, so what I'm going to do is I'm going to take this block and repeat it. So before that, let me pull this down a little. Okay, so let's pull this down a little, pull this one down. Okay, so I'm going to repeat this block as another transistor over here, and I'm going to connect this like this. Done. And then same thing I'm going to do with the pull down circuit. I'm going to introduce another block here, another transistor actually. Okay, so I'm going to do a copy and a paste, and I will paste it over here. So I have added another transistor to the pull down, and I'm just going to give another terminal to this. Okay, and I'll call it C. So this is going to be terminal 6 and I'm calling it C. Okay, so we are done with the 3-input NAND gate. Okay, one more thing is, do I need to scale? You can be the best judge. You figure out if you want to scale this stacked transistors like this. On this side there is no issue because all of these are in parallel, right? So pull up is not going to be an issue. On a pull down you might need to increase the size of these pull down transistors because they are stacked on top of each other. But anyway, I have to just modify this to include one more pin. Okay, so let's say if I can just work with the current setup itself and make a place for another. I'm not sure if I can, but let me see. So I'm going to introduce another pin, and that pin would be C. Okay, so that pin is C. Okay, and another thing which I'm going to do is just extend it to accommodate it. Okay, so now this is a 3 input NAND gate. Okay, you need to name this pin as C also, because otherwise it will not match what you have done in the schematic. Then I'm going to insert an arc just to complete the methods here, and I am going to place this over here. Okay, so we are done with the 3 input NAND gate. Same thing I'm going to copy to a high speed version, right? So this I can say copy cell, and I'll change this to HS and choose the folder to be a high speed NAND gate. Okay, and say okay. So under high speed you will find that. Okay, but I'm going to copy these transistors from here. So this is your FinFETs 7 nanometer, and I'm going to paste them over here and replace each one of them. So basically I need to replace these guys too, but they will fit as is. There will be minor adjustments which you may have to make because you moved the transistors now. Okay, so now this is a 3 input. Okay, just make sure that the connections are okay, right? A, B and C, so they look okay. Okay, so now we have a 3 input high speed NAND gate as well. I'm going to just add a text here which distinguishes it. Right, now I'm going to make a 3 input NAND gate I have got, right? So I'm going to make a flip-flop which is a D flip-flop which is going to be positive edge triggered. So I would say pause trick DFF. Okay, so I have to quickly do something with the feedback with preset and clear. So I need 6 such 3 input NAND gates. Okay, so in the static I'm doing for the medium first. So let me just let me just say file save. I want to rename this because I haven't added the script, so I will just rename it first before. So this is going to be medium speed. Again I'm going to do a new folder here which is going to be medium speed, or okay, and then I'm going to do a new folder called high speed. Okay, this goes into medium speed. Fine, so let's do this one. So all you have to do is take a 3 input medium speed gate, and I would need 2 of them here, and I will connect them. So I need 2 of them over here. Okay, and then I'll repeat them. So basically okay, and let's repeat it. Okay, and I will, so all I need to do is I'm going to do a VDD and ground, VDD and ground. So I have got 2 pins, so one of them I'll name as VDD, sorry about that, VDD, and all these are VDDs. And then I have got ground, so all these are grounds. Okay, so once we are done with this, I'll just add the feedbacks. Okay, so this feedback is done, and similarly I will do the feedbacks for the others, right? One, okay, so we are done with the feedbacks, and then I'm going to have clock preset and clear, right? So let's do the clock first. CLK. Okay, that's the clocking. So this is going to be the gating clock, so it will gate on the positive level. Okay, and then I need clear, preset, and D. So D is very simple over here, so that's D. Correct, and then I need a clear, right? So let's do a clear. And this clear will also gate the other one, right? So this clear is also going to gate this one. Fine, and then I need preset, right? Okay, so this one is also gating this one, and all I need is a clear, sorry, a preset. Okay, it should be preset bar, but anyways, when we'll test it we will know this. let me rename this PRST, smaller names. Okay. Okay, and then you need Q and Q bar. Q. And you have got QB. Okay, I'm gonna figure out whether it's a preset. Okay, most probably these are going to be preset bar and clear bar. Okay, unless I do the simulation. So basically the rationale is this: if this clear is going to be low, then this flip-flop is going to have a high output, right, depending on the state, right? And if this is going to be low, then this is going to be high, so that will be set. So I think they are going to be preset bar and clear bar, right? But I am not going to just speculate. I'll just simulate and see. Okay, so we have a D flip-flop, and there is something missing here. There has to be a connection over here also, right? This is something which is missing. There has to be a connection here too. Okay, so let me make some corrections here. Okay, so this connection is wrong. Okay, okay, now it's done. So because it will be difficult to debug later on, so make correction now itself. Okay, so I'm going to just save this, and I'm going to make a symbol for this. So under flip-flops, I'm going to say new symbol. Okay, and very quickly I'm going to make a symbol for this one. This is all I'm ready to give it. This is going to be edge triggered. This is going to be the D input, and this is Q and Q bar inputs. This is going to be VDD. This is going to be ground. Okay, and I will do a preset over here, and I will do a clear over here, and I assume that is going to be preset bar, but I'm not going to change it till I verify this. So this would be preset, this would be clear, and this is going to be edge triggered, so I am going to put here this. So this is a D flip-flop which is positive edge triggered with preset in clear. Okay, so let's test this D flip-flop. So I will create a new schematic, call it test DFF. Okay, say create schematic, and I am going to copy this. I'm going to just instantiate, so that's the instance of it. Okay, I'm going to attach the supplies rails, so I'm going to operate from 1.8 volt. Okay, I'm going to hold these preset and clear to be high, because then they don't influence my output stages, right? So I will just hold them high. Okay, now I'll give a clock to it and a D input, right? So let's put a clock first. Okay, or rather D input first. Okay, so I'll go to sources frequency domain, and I'm going to put a pulse. I'm going to operate this at 1 gigahertz, so this will be 49, and this will be 01, this will be 01. So that's 1 gigahertz clock. Okay, next thing what I'm going to do is I'm going to put half the frequency, or rather, yeah, half the frequency or 1/4 the frequency. So half frequency or 1/4. So I'm going to do 25, and this would be 199. Correct. So this is going to be my D input, and I'm going to delay the clock by half the cycle. I'm going to delay the clock by half the cycle, so the delay would be 0.5 nanosecond. Correct. And then I'm going to load this with certain capacitance. Okay, load it with 10 femto. Okay, so this is Q bar and this is Q. This is 10 femto and this is 10 femto. Okay, so we are ready with the simulation. All I have to do is label. So this one is D, this one is CLK, this one is Q bar, and this one is Q. And next I'm going to do is from the library files I'm going to have an include file. So I have an include file over here, and I'm going to do transient simulation, transient. So I want 2 cycles of this, so it will be like 4 nanosecond is 1 cycle, so 8 nanosecond. So I'm going to do a simulation transient. I'm going to do it for 8 nanosecond or 10 nanosecond, for example, and step size is the rise time, which is this. So I'm ready for the simulation. So if something goes wrong, then I have to come and correct it. Okay, one thing obviously is wrong is 1.8 volt over here. So this should be 1.8, and this should also be 1.8. Correct. Now let's see. Okay, so we'll have to redo the simulation again because we didn't put here 1.8. Let's see what's taking time. Okay, doesn't matter. I'm going to simulate this again. Simulate. Okay, so I'm going to have D and clock just to be sure that we are okay. Okay, so basically I'm seeing 2 cycles, so I'm seeing 2 rise times, right? So one is this rising time, other is the this rise. So their clock has 2 rise and a D. Now here when it is low, again I have 2 rise. So basically the rising edges is where this D flip-flop is going to respond. Let's put here Q and Q bar. See what happened, and let's separate out these. Okay, let's separate out these. Okay, and I'm going to change. Okay, I'm going to change the scales. So bottom y-axis 0 to 2 in steps of 0.5, and the top is again 0 to 2 in steps of 0.5. Okay, and then I'm going to change this color to green so it's more visible, and change this color to, or make it thicker. Okay, make this one also thicker. So notice that this is working. Okay, why I'm saying this is working? Because Q and Q bar are opposite to each other. That's fine, but then at the rising edge, forget about the first one. Let's look at the second one. At this rising edge, Q has to decline. That's what's happening. Again, at this rising edge, Q will remain the same, but at this rising edge, Q has to change. So basically this is aligned with this on the rising edge. So I was correct that that is a preset and clear bar. Okay, so if you want to clear it, then for example, if I was to run this with this thing over here, then basically that means that its output will be 0 throughout. Okay, so this Q is 0 throughout and QB is 1 throughout. So this is going to be clear. And if I do the other way, where I have to preset it, so I have to hold it low, so this will be set, so Q will be high and Q bar will be low. So Q is high and Q bar is low. Okay, so preset and clear are working properly, and D functionality is also okay. So basically this is a D flip-flop which I just implemented using NAND gates. Now I would make a very quickly a high-speed version, and to do a high-speed version you can very easily just copy and change the labels. Okay, so I'm going to do the following. I'm going to make a copy of this, copy cell, and this is going to be HS. Okay, and then folder is going to be high speed. Okay, done. So I have this one which I'll just modify. To modify this, all I have to do is change this MS to HS, and done. So change all MS to HS. Okay, so this became a high-speed version because I have changed all 6 of them to be HS. Save it. All I'm going to do is change the symbol to add a text here to show it is a HS. So insert a text here, call it HS, and we are done. Now we are going to copy the test bench, copy cell, and I'm only interested in test bench. Okay, I'll rename this as HS and copy it to high speed. Okay, so I have the one over here. All I have to do is okay, I'm going to change this to HS, and nothing changes. I have to change this to, let's say, 3 pico, 3 femto, 3 femto. That's the loading. And then I'll change this to 10 gigahertz. So this will become 49 pico, and this is going to become 1 pico, 1 picosecond, and this is also going to become 1 picosecond, 1 picosecond, and the delay is going to be 50 picosecond, 50 picosecond, and this is going to be 250 megahertz, 250 megahertz, and this is going to be 50, so it will be 200 picosecond, so 199 picosecond, and this is going to be 1 pico, this is going to be 1 pico, right? And I'm going to simulate for 1 nanosecond in steps of 0.1 picosecond, and I need to take out the two models. So I'm going to take this model, Control C, come upstairs, Control V. I'm going to place them here and delete this guy. So I'm ready for simulating a high speed. So in this case, everything looks okay to me. I'll just hit simulate. And I'm just going to copy the display file because I really don't want to do the display again. Control C. So whenever the display pops up, I'll do a Control V. By the way, this 10 gigahertz, you can take this D flip-flop to almost 60 gigahertz. This will work. Okay, almost done. Okay, Control V. Okay, oh, I haven't received this. Oh, this expensive, time consuming. What happened here? What happened to the time period? 10 gigahertz, so this should be 2.5 gigahertz. Sorry, mistake is mine. This should be 2.5 gigahertz. Sorry, let's do this again. So that's why we were supposed to receive other cycles, right? We didn't. But the functionality is proven because on the positive edge you got the transition to positive, and on the another positive edge you got this transition to negative responding to the D. So the logic is very simple. D is equal to sorry, Q is equal to D when the clock, again, so now it's working. Okay, Q is equal to D, okay, when the clock has become 0, or sorry, when the clock has become 1, right, and there is a transition on the clock. So that's the, when we do VHDL, we will say Q is equal to Q is equal to D when clock has become, when clock has a transition or a event and clock became 1, else Q is equal to Q itself, right? So this is the description of a D flip-flop. Okay, so we are done with the high-speed D flip-flop. Okay, so now I'm going to just show you one more way of creating a D flip-flop, and that would be using master-slave transmission gates. Okay, so let's place these in their respective folders. Okay, so now I'm going to make a D flip-flop which is going to be negative edge triggered. Schematic. Okay, so I will say neg trig DFF MS. So MS is medium speed, don't confuse with master slave. Okay, but that's my naming convention. Okay, so how do you do this in transmission gate? As I described the VHDL line. Okay, Q is equal to D. So what do you have to do? I have to take a transmission cell like this one. Okay, let's place this over here. So there is a D input, correct? Okay, so Q would be D when this is enabled, else it will be Q itself. So basically that would mean that I need a latch on the output. So I'm just going to mirror this like this in F5, place it over here like this. Okay, now this one will be the feedback loop, and then I need two inverters, NOT gates, static gates, medium speed, NOT gate. So that's the one. So I need one over here, one over here, and I'll just copy this to here, copy, move the text to here. So we are set. So this will be the feedback loop which will latch. So this path will latch like this, right? Now this is going to respond to positive edge, right? So if I put a clock here, okay, so this is going to be capital C. Okay, so this is a clock. Okay, and then I will put another inverter here to do a clock bar. So this is going to generate a clock and a clock bar. Clock, clock bar. So I'm going to name them. So this is going to be clock, and this is going to be clock B. Okay, so if I want to have a through path, okay, so that means that this should be clock and this should be clock B, and this is clock. Okay, so when clock is high, this transmission gate is through and the D is communicated to Q with certain delay. When clock is high, this path has to be off. When the clock is low, this path, feedback path, has to be on and this has to be off. So this will be in tandem. So this thing would be clock B, a tandem of what happened to the input transmission cell, and this will be clock. This is done. Okay, so this is a master slave block. Okay, so I'm going to repeat this block. Okay, so to repeat it, I'm going to do something else. I'm going to copy this one over here. So now this is in tandem because this is a master and this is a slave, and this one I have to flip it. Okay. Okay, so this is clock B and clock, and these will be as is. Like this, and then this will be in the feedback path. So I'll just mirror it before placing it. So now you see that this is in tandem, right? F5. Okay, so this will be the slave feedback path and forward path. Okay, so it will come here, this will go over here. F5. Okay, so now what is missing? Clocking is done, and then the output is Q. So this is the Q output, and all I need is supply and ground. So I will say I need one pin which is VDD and one pin which is a ground, and then I'm going to name the pins. So this is VDD, and this is VDD, this is VDD. So I'll do all the supplies. Okay, and then I'll do all the grounds. So this will be ground. Okay, so all VDDs and grounds are connected. So this portion is a D latch which responds to positive level, and this is a D latch which responds to the negative level, right? So the D goes through, okay, on a master when it is a positive clock, and D goes through from slave when it is a negative clock. So this is straightforward, and all I will do is I will make a symbol for this, right? So I'll go to transmission gates flip-flops. Okay, under flip-flops you have negative edge triggered, right? Yeah, so this is the one for which we have done. So I'll say new symbol and say okay. Okay, by the way, if you want a bar, okay, so you can always step in a Q bar from here, right? So this is Q bar, because this is Q, this is Q bar. So I hardly need a Q bar anytime, right? So I'm not going to have a Q bar here, but if I want, I can, right? Usually in feedbacks you might require a Q bar, right? But sometimes you have to terminate a Q bar, right? So should I generate a Q bar? In feedbacks you usually require Q bar, right? And if you put an additional gate, additional not gate at the output, it's going to delay. So rather I will put a Q bar also. So QB. Sorry for the confusion. Sometimes I'm thinking ahead of me. Okay, so this is done. So this is going to be Q bar. So I have to generate the symbol again. So this symbol has to be deleted. Okay, so this symbol has to be deleted. Okay, let's make a new symbol. Now we are okay. We are done. So all I need is this guy over here. Like this. This ground goes to the bottom. This VDD goes to the top. this Q bar goes to the left, and this D goes to the left, and this clock goes to the left. But I want to put here details of what this is. So what I'm going to do is I'm going to switch off the grid for a second, create some space for a bubble, put an edge symbol over here. So basically that's the edge symbol, right? Okay, and then I'm going to put a circle like this one over here. So now I have a negative edge triggered. I'll turn on the grid back on. The symbol for the negative edge triggered, D flip-flop. Let's test this. I can test this in the same setup, right? So I'll put test this thing, and this time I'm going to test the master slave negative edge triggered. So I'm going to copy this over here. This guy throws out. This is connected over here. F5. This is connected this way. This is VDD, and this is ground. And I don't need a reset. This doesn't have a reset. You can generate a reset also by a slight modification of the circuit, and that's a clock. Now this is going to be negative edge trigger, right? So the delay I'm going to delete. Okay, I don't want a delay. Okay, so the two transitions. Actually in digital circuit, one thing you have to be sure: two actions in a circuit cannot take place on the same clock if they are dependent on each other. So you have to be very clear. Two actions cannot take place at the same clock edge if they are dependent on each other. So that's the key. Okay, so that's why I don't want a D transition to be same point as the clock transition, because then that is depends on the delay, then it will have unpredictable results. So I don't want that. So once I do simulation, you might come to know what I'm saying. So I'm going to hit simulate. Okay, so that's what I was saying. So there is what I have done is I have avoided the falling edge on the same edge as the D. So there's a falling edge over here, that's fine. So let's look at the second falling edge. It's over here where the transition takes place. So on the falling edges, the transitions are taking place. So the D walks here. Okay, so let's make a high-speed version of it very quickly and test it out. So to do a high-speed version, all you have to do is copy this cell and copy this to change the name to HS, high speed, and copy it to high speed folder. Say OK. So that's over here, and all you have to do is change these names. So this will become HS, this will become HS. So this is very neat. All you have to do is this. We also do in VHDL, right? So VHDL, every sub-circuit is a black box. You can always change the black box. So this is what happens in case of what you call architecture and entity. For any component, you would write a configuration to change entity and architecture pair to represent an instance of a component. So that's what happens in case of VHDL also. Okay, so everything is HS right now. True, everything is HS. So this is done. I will just change the symbol to reflect that this is a HS. So I will insert a text to tell that this is going to be a high speed version. Done. And then to test this, I will go modify the test mesh to test it. So I'm going to take a negative edge triggered D flip-flop over here. do almost the same thing which we did with the other one. Okay, and this 50 pico I don't want for the same reasons. I'm ready for simulation. Testing negative edge trigger T flip-flop at high speed of 10 GHz. So unless I have done some blunder, the results would be same as what happened for the positive edge triggered, right? So that one was based on delays, and this one is based on master slave. And there are hardly any performance differences between the two. So you can always swap them in your design just by changing the name from NAC to POS, and that's it. So you see my naming convention this way, that you change just 1 or 2 letters and you have a new, you just replace the. Okay, so is it working? So on the falling edge I have a transition. Everywhere on the falling edge I have a transition. So this is working. So this is a negative edge triggered high speed D flip-flop clocked at 10 GHz. You can clock this at 60 GHz also, or 80 GHz, it will work. Okay, so now this is the section which I just concluded, and later on what we'll do is we will go to other logic families which are used in digital high-speed digital design. So let me just